The voltage across parallel plate is adjusted so that a charged oil droplet with a certain mass, so it's going to have a weight acting down that way, hangs motionless between two oppositely charged parallel plates as shown. The plates are 20 millimeters apart and the potential difference between them is 250 volts. So this is the roof and this here is the floor, and under ordinary circumstances this oil drop would fall downwards, but it doesn't. It's obviously being attracted to that positive plate, so that is its weight acting downwards, and what holds it towards the positive plate is an electrostatic force. Draw the electric field pattern between the plates. What's important is that you have a uniform field all the way across, which means that it's straight lines and they're evenly spaced. They must go from positive to negative. And then finally, at the ends, you must show the curved electric field at the ends. What is the sign of the charge on the oil droplet? Well, since it's being attracted to the positive plate, it must be negative itself. Identify the forces acting on the oil droplet. I've just done that already, weight and electrostatic force, and they should be the same length because it's in equilibrium. Calculate the magnitude of the weight of the oil drop. Well, they've given me a mass. I need to change that into kilograms first and foremost. So it's going to be 1 times 10 to the negative 12 times by 10 to the negative 3. And then I need to multiply that by 9,8. And I land up with 9,8 times 10 to the negative 15 newtons. And a weight is always downwards, but we are only asked for magnitude, so we don't need to put the down in there. What is the magnitude and direction of the electrostatic force acting on the oil droplet? Well, it's going to be exactly the same magnitude, except that it is going to be upward. We've got 2 microcoulomb charge is placed as shown in the sketch, and it causes an electric field that's given to me at a certain distance. Sketch the shape of the electric field about the 2 microcoulomb charge. You need to use a ruler to make a nice little star, and because it is a positive charge, the arrows need to point outwards. Explain in terms of force and charge what is meant by electric field strength. Newtons per coulomb, so it is the force exerted. It's this 1,8 times 10 to the power of 6 newtons of force are exerted on each coulomb of charge. So it's not difficult, it's just knowing what they want you to answer in that. And then determine the magnitude of D in centimeters. That's just a substitution. E is equal to KQ over D squared, or R squared if you prefer, but it's D in this case. And we've been given the electric field strength 1,8 times 10 to the power of 6, and that's equal to 9 times 10 to the power of 9. The charge given is 2 times 10 to the negative 6 because it's microcoulombs, and we then need to square root my answer, and we land up with 1 times 10 to the negative 1 meters, which is really equal to 0,1 meters, which is equal to 10 centimeters. For resistors of different resistances are connected in the circuit below. Actually, there are only 3, which is rather sad. The battery has an EMF of 30 volts, and the resistance of the connecting wires is negligible. What is meant by EMF? It is the total energy a battery can supply to each coulomb of charge. Don't use shortcuts, please, because you never know what the final examiner is going to think. What is the total resistance of this circuit? You first work out the parallel part. So 1 over R parallel is equal to 1 over 6 plus 1 over 4, and therefore that is equal to 5 over 12, and R parallel is therefore equal to 12 over 5. You're supposed to give your answers in decimals, so you must do that. So it's 2,4 ohms. Plus the 18 ohms. So in total, that's 20,4 ohms. Calculate the current flowing through the battery. So I is equal to V over R. There's no internal resistance in this particular circumstance, so it's 30 divided by 20,4, and that's going to be equal to 1,47 amps. What is the current in the 4 ohm resistor? Well, now we've got a little branch. We can do a ratio, or we can put a pretend voltmeter over here, and then we can say, using this current over here and the 2,4, we are able to multiply them together and get a potential difference of 3,53 volts. And from there you can say current is equal to V over R, 3,53 for the parallel network. The resistance of the 4 ohm resistor is 4, and you land up with 0,88 amps. You could also have taken your 1,47, divided it by 10 and multiplied by 6. What would the effect on the main branch current be in the following situations? You only have to answer increase, decrease, or stays the same. An additional 100 ohm resistor is added to the parallel connection. That will decrease resistance, but they want main branch current, so it's decrease resistance, but that means increase the main branch current. You don't have to say why. And the addition of a 30-volt battery added in parallel, that would be exactly the same, and it would make no difference to the circuit at all, except that it would last longer. And the reason it makes no difference, by the way, is because they've got no internal resistance. If they had internal resistance, actually it would increase the current on the main branch, because in essence we would have been adding a parallel resistor to that. 3 electrical devices are X and Y, and oh my gosh, Z is not there, are connected to a 24-volt battery. So there isn't a Z over there. With internal resistance R, as shown in the circuit diagram below. The power rating of each of them was indicated in the diagram, and with the switch S1 closed and the devices function as rated. If the power rating of resistor X is 100 watts and the potential difference across resistor X is 20 volts, then calculate the current flowing through resistor X. So all we're going to do is we're going to say power is equal to V times I, 100 is equal to 20I, and therefore I turns out to be 5 amps. Calculate the current flowing through resistor Y. Now, if 20 volts is on this branch of the network, then that means that 20 volts must be on this branch, because the entire branch must be 20 volts as well. So we can say power is equal to, 150 is equal to 20I, and therefore I turns out to be 7,5 amps. What is the total resistance of the external circuit? So we're going to say, what is my total current? Well, my total current on the main branch is now going to be 12,5 amps. And then we can say R external is equal to V over I. And externally, obviously, we're only delivering 20 volts. The current is going to be equal to 12,5. And therefore, I land up with 1,6 ohms in the external circuit. And the internal resistance of the battery, well, R internal is going to be potential difference internal divided by current internal, and the internal potential difference is 24 minus 20, which is only 4. The current going through the battery is going to be this 12,5, and therefore we land up with 0,32 ohms. Annabelle builds a DC motor as shown below. She's made several mistakes and the motor doesn't work. So, identify 2 mistakes. Well, the first mistake that's been made over here is, quite frankly, we haven't got a power source. This isn't connected to anything. Also, these turns of wire have been done, they're in an orientation where they can't spin perpendicular to the magnetic field. Some of you said that the magnets were both north. Well, the north is on the left there and on the left there, which means you've got a south over here, so that wasn't a good thing. the coil has not been linked in any way to the split ring commutator, which also makes no sense whatsoever. Okay, so there is a split ring commutator, there is a coil, and there are magnets, but they are absolutely incorrectly linked to one another, and they don't have a power source at all. So she's going to correct all the problems, and then she attaches a lifting mechanism to the motor, which lifts a mass of 5 kilograms through a certain distance. So what is the power output of the motor? Well, power is equal to work done divided by time. So I'm going to go mgh divided by time. 5 kilograms, 9,8. Height is 50 centimeters, which is 0,5 meters. And divide that by 2 seconds, and I'll end up with 12,25 watts. Assuming 100% efficiency of the motor, if the motor is attached to a 12-volt battery, what is the resistance of that motor? Well, power is equal to V squared over R, and therefore we can say 12,25 is equal to 12 squared divided by R, and R turns out to be 11,76 ohms. The diagram below shows a simple electrical generator. What type of a generator? Is it AC or is it DC? It's got a split ring commutator, which means it is a DC motor. Why? Because it's got a split ring commutator. State the direction of the current, clockwise or anti-clockwise, through the light bulb. You now need to use your right hand motor rule. You're turning this coil in that direction over there, which means this arm would be coming up and this one would be going down, going from north to south using your right hand. And what it turns out as is that the current is going to land up, going in that direction over there. So it is anti-clockwise. And referring to the diagram, state the position, vertical or horizontal, where the induced current is going to be at its maximum. Where is the most cutting going to be happening? At the point where it turns over here, when it's coming across the magnetic field. Because if you think about it, your magnetic field lines are going like this. So at the point where it cuts across those magnetic field lines in that direction, when the coil is cutting across that way, you're in the vertical position. So that is going to be your moment where you have the most cutting. ESCOM uses AC generators to produce electric current delivered to the power grid. What is the advantage of using AC power generation with respect to power distribution? It allows, you need AC for transformers to work. And because AC gives you a changing magnetic flux. And then what is the advantage of that? It is the fact that we can step up and step down current and potential difference and allow for efficient power movement, because we can make the voltage very high and the current very low when it moves through wires over far distances. In a step-down transformer, ESCOM steps the voltage down from 100,000 to 500. What ratio must the number of coils be to achieve this? Well, if it's, sorry, it's not 100,000, it's 10,000 to 500 is 20 to 1 in terms of a ratio of coils. We've got an apparatus shown here to investigate the photoelectric effect. The apparatus shows both frequency and intensity of the incident radiation can be changed. The type of metal and the voltage across the electrodes can be adjusted. So it's quite a lot like the FET simulation, really. A source of bright red light and dim blue light are shone on the surface of the metal for the same length of time. In both cases, electrons are ejected. The wavelength of the blue light is 440. Calculate the energy of a photon from that blue source. First thing I need to do is I need to establish the frequency of that light. So F is equal to C divided by lambda, and that is 3 times 10 to the power of 8 divided by 440 times 10 to the negative 9. And then we have got 6,82 times 10 to the 14 hertz. Then its energy is equal to HF. So I'm going to take that frequency and multiply it by 6,6 times 10 to the negative 34, and I land up with 4,5 times 10 to the negative 19 joules. The switch is closed. What happens to the current reading on the microammeter if the dim blue light is changed to bright blue light? Write only the word increase, decrease, or stay the same. You're going to land up with more electrons. Because it's beyond threshold frequency, it will increase the current strength. Explain why the maximum kinetic energy of the electrons ejected by the faint blue light is greater than the kinetic energy from the bright red light. So Emax, the energy or the kinetic energy maximum, is directly proportional to frequency, not brightness. And therefore, blue has got a greater frequency than red. And therefore, it will have a greater Emax. And then the table shows the work functions of selected metals. There they are. Calculate the threshold frequency. Remember, you've got to change that electron volt value into joules. So first, that's the first thing. So my work function is equal to 2,75 times 1,6 times 10 to the negative 19, which is my conversion factor, and I get 4,4 times 10 to the negative 19 joules. Then I can say that my threshold frequency, WO, is equal to HFO, and I can put the 4,4 times 10 to the negative 19 in, 6,6 times 10 to the negative 34, and then I divide through and I land up with the threshold frequency is 6,67 times 10 to the 14 hertz.